This is chapter 6.4, and this is applications of linear systems. So basically what we're doing is you're not really learning anything brand new. You're taking what you've learned in the last 3 sections and applying it to like real life situations and word problems. So your job is going to be to pick which method is best for solving these systems of linear equations. I would definitely suggest writing down this entire chart. So when to use them, graphing is really not anything that's very exact. It's used more for estimating, unless of course you have a graphing calculator. Then you can be very exact with it because the graphing calculator will give you the exact XY coordinates for you. But if not, you'll want to focus on either substitution or elimination. Substitution's best if it's real easy or if you already have one of the equations solved for one variable. And elimination is best when the coefficients are the same or opposites, and when it's going to be easy to eliminate either your x or your y. All right, so the first one, a fashion designer makes and sells hats. The material for each hat costs $5.50, and the hats sell for $12.50 each. The designer spends $1,400 on advertising. How many hats must the designer sell to break even? So the best thing to do is decide, okay, what are my variables? And we usually deal with an x and a y. And remember, your x is your independent, and your y is your dependent. But that doesn't necessarily mean that you have to stick with an x and a y. If you want, you can change them. So what are the 2 things that we're dealing with for this problem? Well, we are dealing with money, and we're dealing with how many hats. How many hats, and break even meaning money, right? How much zero make your money back, okay? So instead, I'm going to deal with H, and I'm going to use M. So we got H is going to be my hats, and M is going to be my money, okay? And now we have to write 2 equations that work with the information we have. Well, the first thing is how much money, the money basically that you've spent will equal $5.50 per hat. So M is going to be $5.50 per hat, plus you spent $1,400 on advertising. Okay. The other equation is the money that you'll make. So it's the money that you've spent and the money that you'll make. And the money that you'll make is $12.50 per hat you sell. So right now we have 2 equations. Both of them are solved for M already, so it's really easy. We're going to use substitution for this. So you pick either one of them. I'm going to pick this one, and I'm going to replace this M with $12.50 per hat. So we now have $12.50 per hat equals 5.5 H plus 1,400. I subtract 5.5 H from both sides. That gives me 7H over here and $1,400 over here. Divide by 7, and H equals 200. So what that means is we need to sell 200 hats in order to break even. Now, how much money would that be if we do sell 200 hats? So you could plug that back in. So take your H and plug that back into either one. I'm going to take it and plug it into the simpler of the 2. if we take 200 times we get $2,500. So basically, it costs $2,500 to kind of kickstart this, and once you sell $2,500, that's your break even point. Once you sell 200 hats, that'll be $2,500. That'll be your break even point, and now any hat after that, you'll be making money. Okay. A puzzle expert wrote a new Sudoku book, puzzle book. His initial costs are $864. Binding and packaging each book costs 80 cents, and the price of each book is $2. So again, what do we want to stick with? Well, we're dealing with books, like copies, so maybe we'll call them copies. And again, we're dealing with money. So the money that this puzzle expert will make is $2 per book, or $2 per copy. So there's one equation. And the second one was how much money did it cost for them to kind of get going? Well, it's 80 cents per copy to bind it and package it, plus $864 to do whatever. Time, advertising, whatever they're doing to get kind of started. And again, we have both equations are solved for M already, so we're going to use substitution. So I'm going to replace this M with this 2C. So we have 2C equals 0.8C plus 864. Subtract 0.8C from both sides. You get 1.2C equals 864. Divide by 1.2. And 864 divided by 1.2 gives you 720 copies of the book. Is the break-even point. And again, if you want to find out how much money that is, just plug it back in, but it doesn't ask you for that. Local zoo is filling 2 water tanks for the elephant exhibit. One water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. Second water tank contains 29 gallons of water and is filled at a constant rate of 3 gallons per hour. When will the 2 tanks have the same amount of water? So we need to write 2 equations for this. I'm going to go back to X and Y, just because that's what's most common. So X, I'm going to refer to the time. So that's going to be the number of hours. And Y is going to be how many gallons is in the tank. So gallons of water in the tank. So how many gallons are in the tank? Well, that will be depending on how long we filled it. So the first one is 10 gallons per hour, which is X, plus 50 that were already in there. Second one is 3 gallons per hour, plus 29 that were already in there. So again, our best method for this would be just substitute. So replace this Y with that. So we got 10X plus 50 equals 3X plus 29. I'm going to subtract 3X from both sides. Subtract 50 from both sides. So these canceled, and I am left with negative 21 over here. Divide by 7. And X is negative 3. So it's asking for when will the 2 tanks have the same amount of water? And we get an x of -3. Now, does that make sense? In -3 hours, does that make sense? And it doesn't. Okay. If you plug x back in, what you actually get is a number of gallons of 20, and that's not actually possible because neither of those tanks had 20 gallons in them to begin with. They were both more than 20 gallons. One was 29, one was 50. If you're adding water, how are they ever going to get to 20 gallons? And so that's not possible. And so therefore, this would not be a viable solution. And so this is basically a not possible type of answer. Or you could call it a no solution, right? And actually, let me cross that out. It is a solution. I'm sorry about that. It is a solution, but we'd have to go back in time in order for that to happen. And so it's not viable. Put it that way. It's not a viable solution given what we've been giving. Okay. Last one. A traveler flies from Charlotte, North Carolina to Los Angeles, California. At the same time, another traveler flies from LA to Charlotte. So the other way around. The airspeed of each plane is the same. The ground speeds are shown here. So the airspeed is, it's kind of like if you were to set your cruise control for your car. Or just put it this way, set your foot on the pedal. Now, when you hit a hill, if you don't push your foot down anymore, your car is going to end up going a little bit slower. And if you're going down a hill, your car is going to end up going a little bit faster. This is the same with these planes. So their airspeed is set to go in a certain amount. But because of the wind, their ground speed is actually going to be different, right? So let's try to write an equation based off of this. So we basically know that if we take the air speed plus the wind speed, that's how we'll hit the ground speed. So again, the airspeed's set, and if the wind is pushing them, it's adding to it, right? So it says A is our airspeed, W is our wind speed. So plane one, if we take A plus W, because again, the wind right here is pushing it, we're going to get 550 miles per hour. But this plane right here, this wind is going against it. So we have technically its airspeed minus the wind speed is giving it 495. And again, the reason I'm using a minus sign instead of a plus is because this plane was being pushed by the wind. This plane was being right there. That plane is getting pushed against. Okay, so one has it at its back, one has it at its front. Here, so what we have now is we have two W's, a positive W and a negative W. And they all have exponents, or coefficients, I'm sorry, not exponents. They all have coefficients of 1. But since the W's are already opposites of each other, we're going to use elimination. So I'm going to take the Charlotte, North Carolina plane and put that equation underneath the one coming out of LA. And I'm going to add these two equations. So 1A plus 1A is 2A. 1W minus 1W is going to cancel each other. And if we add that up, we got 5, 14, 1,045. 1,045 divided by 2. And we get A equal to 522.5. And we're looking for airspeed. So this is going to be in miles per hour. Now we want to know so that's the airspeed, what they're looking for there. They also want us to find the wind speed right there. So we simply plug it back into either one. I'll plug it over here. So we've got 1 times 522.5 minus 1W equals 495. We've got our minus 1W. Let me subtract 522.5 from both sides. Those cancel. We're left with negative 1W equals, that would give us negative 27.5. And just switch the symbol or multiply each one by negative 1, and you get W equals 27.5 is our wind speed. And so there's your solutions to what's the airspeed and the wind speed. Okay, those are some of the things that you'll be dealing with in this section.